Hello everyone, I'm Mo Sabbir, a second-year PhD student at the Computer Science and Engineering Department of University of South Carolina. Today, I'll be presenting our paper, A Case for Temperature-Aware Scheduler for Millimeter Wave Devices and Networks. I've divided my presentation into 5 distinct sections. I'll begin by explaining what necessitates a completely new technology for the next generation wireless networks and why millimeter wave is a suitable choice. Next, I'll introduce our audience to the phenomenon of device overheating in millimeter wave networks, a quite prevalent and yet unstudied phenomenon. I'll then be presenting the results we obtained from thermal characterization study we conducted on a 60 GHz millimeter wave mobile testbed. Following thermal characterization, I'll present Aquilo, which is an antenna scheduler for multi-antenna millimeter wave systems as a means to combat device overheating. Lastly, I'll conclude this presentation with a brief discussion of our findings and contributions. So let's see why 5G requires a complete overhaul of our wireless infrastructure. The demand for wireless data is not only at an all-time high, but it is projected to increase exponentially in the coming decade. By the end of this year, it is estimated that the number of 5G subscriptions will reach 190 million and increase by 10 times in the next 4 decades. The simple reason is the increasing ubiquitous wireless connectivity of our everyday items from smartphones and tablets to cars, TVs and refrigerators. The overwhelming web of wireless nodes of everyday items is what is being dubbed as the Internet of Things or the IoT. The increasing wireless connectivity imposes several stringent requirements on our wireless networks, namely multi-gigabits per second throughput to support all these increasing wireless nodes, and an expanded bandwidth and ultra-low latency both to support all the new applications coming into the wireless networking realm. For examples, the immersive virtual and augmented reality demand more than 5 Gbps wireless speeds and sub-10 millisecond frame transmission latency. An autonomous car at its peak rate can locally generate 10 Gbps data from its various sensors. All these requirements necessitates a new enabling spectrum. If we look at our current microwave spectrums, namely the LTE and Wi-Fi, bands at 2.4 GHz and 5 GHz and such, this is how much we have in terms of bandwidth. This supports sufficient throughputs for 4G networks, but not so for 5G. Compare this to the much wider, almost hundreds of times larger available bands of unlicensed spectrum. This is what we call the millimeter wave, alluding to the order of wavelength in this band of spectrum. This band supports multiple Gbps and enable the ultra-low latency connectivity that we desire for 5G. Specifically, this blue slice of almost 7 GHz within this large band is being incorporated into the latest IEEE 802.11ad standardization. Just as with any new technology, incorporating millimeter wave into the wireless networks has meant overcoming several challenges. Research in millimeter wave has been going on for a while, and most of these challenges have sound research background in the existing literature, except the overheating of millimeter wave devices. In fact, our investigation with a 60 GHz Rogue smartphone reveals temperature starts increasingly on power up. In this setup, we demonstrate how the temperature of the outside surface of a 60 GHz Rogue smartphone increases through a reel we obtain from a thermal camera. The white circle shows the location of the 60 GHz antenna. Heat distributes from the antenna region over the entire surface of the device immediately on power up. There is already 7 degrees increase in temperature just within 2 minutes. And by 5 minutes, temperature can reach abnormally high, almost 11 degrees above the resting temperature. Indeed, overheating of millimeter wave devices has been reported by several tech outlets, specifically in the last 1 year, showing us clearly that there is a research problem at hand that needs to be solved right away before 5G is widely deployed. The issue with device overheating is twofold. Firstly, the overheating of devices used near face and brain imposes potential health hazards as well as causing user discomfort. Next, the network performance is also degraded as the higher temperature causes a higher noise and leakage current, leading to large fluctuations in the throughput. Despite such prevailing issues with device overheating, the characterization of thermal behavior of devices under millimeter wave network is non-existent in the literature. Hence, we carried out, for the first time in literature, such an investigation on our mobile millimeter wave testbed. Let's check our findings. Our measurement testbed consisted of a Nighthawk X10 router as access point and an Asus ROG smartphone as the mobile node, both capable of working on the 60 GHz spectrum. The setup allowed us to transmit data packets from the AP to the smartphone and measured the corresponding system throughput achieved as well as the resulting temperature of the smartphone antenna chip with fine granularity. Indeed, our measurements have revealed quite large fluctuations in throughput while network strength remained largely stable. In one measurement over 90 seconds, the throughput series showed standard deviation as high as 240 Mbps, while the net strength of the link at which the throughput was achieved remained steady at -64 decibel. While we have seen that temperature remains steady at 47 degrees, 48 degrees region in the idle powered on state, it keeps increasing with data transfer before plateauing off at a higher temperature. The higher value at which the temperature plateaus off increases with average throughput. In order to study the dissipation of the stored heat, we carried out several trials with fixed periods of transmission, and then allowed the devices to cool down. We show here one such 10-second transmission trial. It is seen that while temperature increases rapidly with the beginning of transfer, it does not fall back immediately. Rather, heat in the antenna acts as charge in a capacitor. Moreover, our studies indicate that both the rising profile and the falling profile of the temperature can be modeled as separate exponentials, an exponential rise and an exponential decay. A naive way to prevent overheating of a device is to induce idleness in between periods of data transfer. The idleness allows the antenna chips to cool down. We investigated such a scheme. The AP transmitted packets for 10-second intervals repeatedly, interleaving 5-second idle period in between each transfer. The total operation time was 270 seconds, thus the effective period of operation was 180 seconds. We compared this with a 180-second continuous operation and a 270-second continuous operation. While the continuous operation caused the temperature to reach 75 degrees Celsius within 150 seconds, the trial with periodic idleness never crosses the 65-degree mark. Such a naive scheme, however, is inadequate for two reasons. First, even small transfer duration and high idle period cannot substantially reduce the peak temperatures. Moreover, latency critical and throughput hungry applications require continuously high throughput. These applications such as virtual reality, real-time gaming, or tactile internet with their requirements of high throughput and low latency do not allow buffering of their data. Data transfer is required on demand. Thus, to allow an antenna to periodically go to sleep mode while preventing any idleness in the data transfer, we must switch operation between multiple antenna units placed on the device. Fortunately, this is the likely reality in the coming days as multi-antenna design is increasingly being suggested by industry experts as the means to improve network reliability in the reality of rampant signal outage. Aquilo achieves this switching scheme between the antennas in a smart way so as to achieve the most reduction possible in temperature without causing throughput to drop below the application requirement. The switching is achieved on a temperature awareness basis. The switching of the antenna units is not naive, neither a simple random switching nor one that maximizes throughput by always selecting the antenna with the best link can achieve any near optimal temperature reduction. Furthermore, there are two challenges we must confront. First, millimeter wave channels are very unreliable as signal outage is very frequent due to both blockage and node mobility. While this has made the multi-antenna design attractive, which is good news for us, but this also means that one cannot simply schedule antenna in terms of temperature optimality. For example, just the tip of the user's hand can completely kill link connection. Secondly, our investigation reveals that a completely predetermined temperature model cannot be derived. For the same device, temperature model is highly dependent on the surrounding temperature as well as insulation condition and user handling. As is shown by these example thermal profiles we obtained with the same device at two different locations, an office environment and a home environment. Clearly, the thermal profile obtained from home shows both faster increase and faster decrease in temperature. These challenges imposes us to design Aquilo with these design requirements. Let us see what each of these components achieve. The online thermal profile estimation is the estimation of how temperature at each of the multiple antennas rises during transfer or falls during idle period. Our investigation reveals that this rise and fall can be modeled with separate exponentials. An exponential gain for the section with data transfer and an exponential fall for the section in idleness. The model parameters in Aquilo are derived from online measurements of both the active and the resting antennas in the background. The online estimation of thermal profile helps Aquilo to estimate the peak temperature that would be reached by each combination of antenna schedule. Aquilo executes just that task, generating a list of lookahead schedules with their respective peak temperature. For instance, in a system with 4 slots, this is a likely list of lookahead schedules. So this is how the tasks are scheduled in Aquilo. The lookahead schedules generated at an earlier frame are sorted at the beginning of a later frame. The sorted schedules are used to schedule the antennas in each slot of the later frame. Note that during the sorting process between the two frames, data transfer does not have to stop and hence it does not cause any latency. The only source of latency in Aquilo is the beam alignment of the antennas at the beginning of each slot. One rule that Aquilo follows in generating the lookahead schedules is the non-adjacency criteria, which states that no antenna can be scheduled in consecutive time slot. Hence, the first two schedules on the left are valid. The third schedule is invalid as antenna 3 is scheduled in both second and third slot. Fourth schedule is valid as well. This criteria helps to reduce the size of lookahead schedules by eliminating those schedules which do not allow an antenna to go to sleep mode right after an active mode. Let us now compare and evaluate Aquilo with other antenna scheduling schemes. The most logical antenna scheduling scheme would be one that optimizes the throughput. Hence, we first investigate how much peak temperature can increase in a throughput optimization scheduler. We see that throughput optimizing scheduler causes the peak antenna temperature to rise as high as 70 degrees just within 90 seconds of operation. While average throughput is maximized, the resulting fluctuations degrades network performance. Then we investigate how much peak antenna temperature can increase with Aquilo under the same set of conditions. Aquilo keeps temperature within a tolerable 55-degree range, achieving a reduction of 16 degrees compared to the throughput optimization scheme. Note that Aquilo achieves this temperature reduction, maintaining the minimum required throughput level. Hence, the sacrifice in not following a throughput optimal scheme does not hurt the running application. We carried out further investigations to compare Aquilo with several other antenna switching schemes to see how much temperature reduction is achieved. We first ran a best case impractical antenna scheduler which searches through every possible schedules and choose the one generating the least peak antenna temperature. We then run a random switching scheme which, as the name suggests, randomly selects any one of the antennas at each slot. Then we run switching scheme which randomly selects an antenna but maintains the non-adjacency criteria, a design component of Aquilo. We run this scheme to determine the temperature reduction capability of non-adjacency criteria itself. Finally, we run a switching scheme which schedules the best link strength antenna and thereby maximizes the link throughput. We compared how much temperature reduction is achieved by Aquilo in relation to the other schedulers by running each of the schedulers for several trials. We first compare Aquilo with the best case scheduler. We see that Aquilo achieves temperature reduction just within 1 degree of the best case most optimal scenario in 50% of the trials. Then we compared Aquilo with the other antenna schedulers, showing us clearly how much temperature improvement can be achieved by Aquilo over these other schedulers. At the same time, we computed how much throughput is achieved by each of the schedulers. First, Aquilo's throughput is compared with an throughput optimization scheme. We see that the sacrifice in throughput by Aquilo is only up to 10% for 50% of the trials. Then we compared Aquilo's throughput with those obtained from the other schedulers. We see that Aquilo's throughput very much matches the throughput with the other schedulers. While Aquilo achieves minimization of antenna temperature, it may do so at the expense of some throughput. Some applications, however, require continuously high throughput. We tested running some of these applications such as FTP and VR under Aquilo. We first check the throughput performance of Aquilo, showing us that Aquilo, while minimizing the antenna temperature, also ensures that the applications run with their minimum throughput requirement. Then, in terms of temperature reduction, we see that Aquilo achieves substantial reduction in antenna temperature compared to the other schedulers. To summarize this talk, in all, we have come to the following insights and achieved the following contributions. We have seen that overheating of devices under millimeter wave networks is quite prevalent and poses potential health hazards as well as degradation of network performance. Moreover, we have seen that such an issue is not a trivial problem to solve due to both unreliable network connectivity and the infeasibility of deriving a deterministic temperature rise and fall model. We have based our solution to above problem to a thorough study of the thermal characterization of devices under millimeter wave networks, which is the first of its kind in known literature. Based on our insights, we propose Aquilo, a temperature-aware multi-antenna scheduler for millimeter wave devices. We have seen that Aquilo achieves substantial reduction in chip temperature within 1 degree of the best case most optimal scheduler, while at the same time supporting the requirements of throughput of the running application. Thank you all for listening. We thank our sponsor, National Science Foundation. Please check out our full paper at the ICNP website.